Hello guys, welcome once more to our YouTube channel. Today we are looking at Northwest Mock 2023 physics. We are continuing our revision process and we hope that you enjoy some physics before going into rock physics on Thursday. Let's go. Guys, you know what we do, right? So pause the video, check out the problem and then see if you can solve it. Let's go. State Newton's third law of motion. All right. So to every action force, there's an equal but opposite reaction force, right? Easy. B says a helicopter hovers in still air away from the ground. The mass of the helicopter is 5,000 kilograms and the diameter of the rotor blades is 8 meters. Calculate the speed of air projected downwards by the blades given the density of air is 1.3 kilograms per meter cube. Okay, so this is a very important statement I've made here. The time rate of change of momentum imparted to the air equals the force the chopper exerts on the still air. Why? This comes from Newton's second law now, that the time rate of change of momentum of a body is directly proportional to the force applied on it and takes place in the direction of the force. So the blades of the helicopter are rotating, and so they are imparting a certain change in momentum in the air around it. Okay, around the still air. So you notice that since the air is still, according to the examiner right here, look at this, helicopter hovers in still air. Good. So our change in momentum there, the time rate of change of momentum there is the force. I notice that our u is basically 0, right? Because initially the air was still. So we can get the change in momentum like that. And so you notice that, well, mass there is density times volume. Okay, so how much mass of air do we pump down? It's basically the density of air multiplied by the volume of air that is being pumped, right? So you then notice that, okay, so the volume of air right here is basically the area of cross section around the blades, because remember that the blades are spinning to blow that air down. So the cross sectional area of the blades, the spinning blades, multiplied by the length of the air column underneath the blades. Okay, so you get the volume right there, and then the density, where L is the downward displacement of the air currents, right? So you can get the volume of air that's being moved like that. So you can simplify this. Okay, so rho AV, then we have L over T here. But what is L over T? Is a distance covered by the downward moving air divided by the time, and that gives you what? The velocity. And so you get rho AV squared right there. So we have used Newton's second law to derive an expression for the force experienced by the air in terms of its density, area of cross section of the blade, and the velocity of motion of the air. So we can put in these things. The area, the density is 1.3, area is pi d squared over 4, right? Because it's a circular area that the blade squared across. And then the volume, the velocity there is v squared. So from Newton's third law, of course, you understand that F equals to mg, right? So the force that the blades of the helicopter exert on the air would be equal to the force that the air exerts on the helicopter, and basically that should be equal to the weight of the helicopter, right? Since we're talking about a hovering helicopter, so it just hovers. So if you make this a subject, so F equals to mg, take this F equals to mg and put it up here. Okay, so if you put it up here, in place of F, you put mg, you have 4 mg here. You multiply all through by 4, and then you divide by 1.3 pi d squared. So you have 1.3 pi d squared there, that you have made v squared the subject. Take the square root, you get that. So our v is this. So you notice that our velocity is 27.4 meters per second, which is about 27 meters per second. And that is our answer.